Yeah, we're going to take notes. We aren't going to get through everything. Most likely there will be no homework. I know it's going to be bumming you out. But we're going to just start it, and then we'll have work time for some homework on Wednesday. Okay? All right. Perfect.
So, chapter 18. We have 10 chapters left. We've got through 17 already. All of the remaining chapters, like I said, focus on using this idea of what a sampling distribution is. So we want to make sure you have a really good understanding to help you for the rest of the year. So right off the bat, write down this definition. Sampling distribution. It's a distribution from the results of several samples. That's exactly what we just did. And by a distribution, we mean, think about distribution, think about a histogram. Right? So in other words, a sampling distribution would be exactly what we did.
Each one of these dots represents one of your samples. In this case, it was 5 beans. Okay? And in this case, there was 20 beans, and we wanted to find out what the percent of brown was. So if we're looking at the 5 beans, what would you say, just by looking at that, what do you think the average of percent of brown was? What was the percent of brown by just looking at this distribution? 20%. 20%? Why do you think 20%?
That's the mode.
Okay, looking at the mode. Looks like they're both about the same on each side here, so I'd say 20% was that's a good estimate. Okay? If you look over at our class, is that pretty similar? Yeah, I'd say 20% is a good estimate. Okay? What about for the 20? Sample size is a little bit bigger now. 20 of them. Kind of compare. What do you think? Is it still 20%? No? What do you think it is? Just looking at what we're trying to find out is the average. Well, the percent here is 20. What do you see? 15? Josh, what do you think?
Between like 15 or 20.
15 or 20? What about the other class? Looks like maybe 25-ish. A little bit, maybe between, closer to 25. And that could happen because the beans might not be the same. Okay? Do you notice anything different about these two distributions? Just anything. What catches your eye right away? What do you see?
Well, that one's more skewed and has more variance.
Okay.
Good. So the one with 5, right? You said more skewed and more variance, like more spread out. Good. Which one's more accurate then, do you think? 20. Does that make sense? So conceptually, just make sure this is the first step. If I said to you, hey, go find out what percent of Mr. Murphy's beans are brown, and you went to take a sample, and one person took a sample of 3, and one person took a sample of 100, who's going to be more accurate? 100, you would think, right? In theory, they should be more accurate. So as n gets bigger, they should be more consistent. But when we're done, if you take a nice random sample and you have a good n, look what happened to the sampling distribution. How would you describe, go back to the very beginning of when we started the year, describe that distribution with n equals 20. Say it again. Heard some people say
It's skewed.
it does look a little skewed, right? But in general, looks pretty unimodal, doesn't it? You could maybe be a little skewed to the right. I don't know, Mr. Murphy's mine looked out, actually his looks a little better, right? If you look at his, unimodal, that's pretty darn symmetric. What kind of a distribution do we call that?
Normal.
A normal distribution. And if we had n is 100, if we asked you to take 100 beans in each one of your samples and graft it out, what do you think the difference would be there?
More normal.
Even more normal. All right? So that is a really important concept. The bigger the sample size, the more normal that distribution is going to become. So just kind of recap what we did here. We had our box of beans. Let's say we took out 20 beans, so that's n. N is how much is in your sample. And if I told you from the beginning, because I filled that box up this morning and wrapped it up, gave it to him for his birthday, if I knew exactly before I put them in, I counted them and I said, okay, there are 27 beans, dark brown beans in that box, that would be P. What do you think P stands for? Probability, right? Probability of success, using it all along. So if I told you 27% of the beans in Mr. Murphy's box are dark brown, and I asked you, what's the probability you go in and you grab a bean, what's the probability that is dark brown? What is the answer, everybody?
27%.
Yeah, that's easy. 27%. What's the proportion of dark brown beans in that box? Isn't that amazing?
Yeah.
You guys are so trained to the word proportion. When you hear the word proportion, you think of cross multiply to divide or the fixed fish trick or whatever, right? Don't think about that in stats class. The word proportion means what portion, what fraction, what percent. If I say to you what proportion of the beans are brown, that's the exact same question as what percent are brown. So what proportion are dark brown? 27%. So if I say what percent are dark brown? 27%. What's the probability you get a dark brown one?
27%.
And what's the proportion?
27%.
I know you think I'm weird, insulting your intelligence, asking you the three questions, the exact same question, but all of you at one point are going to ask us, Mr. Murphy and I, that same question. How do I find the proportion? They told me they're 23% are brown. How do I find a proportion? It's the same thing. Okay? So from here on out, when we deal with problems in stats, we like to say proportion instead of percent. So you're going to get proportion problems and you're going to get average or mean problems. All right, make sure you know the difference. So that's P. What would Q be? It is 73%. What does it stand for? Yeah, probability of failure. In this case, the percent of not brown. It's either brown or not brown. Perfect. Okay, so that was N. We're going to take out samples of, so we took out, we're going to take out 10 samples. And when we're done, we're going to graph it and see what we get. And we did that multiple times. Each person did 10. There was probably, when you think about it in here, 7 groups maybe, so there was like 70 dots up there all together. And when you're done, you're going to get a distribution. So we did the same thing over and over and over and over and over again. Does that make sense? And right around here in the middle was the 0.27 or 0.25 or whatever that average is going to be. It should be right around what it's supposed to be, 27%. This is exactly what is happening now with all those darn political polls that I'm sure many of you are getting sick of hearing about. Now think about this conceptually, okay? So, first primary, Iowa. They go down to Iowa, and people get paid to do this by the candidates, and they go in and they try to find out, let's say, what percent of the people are going to vote for Donald Trump in Iowa. Okay? Now, how do they do that? Do they ask everybody in Iowa? They certainly aren't going to ask everybody in Iowa. What are they going to do? Yeah, they're going to take a sample, right? Now, what do they got to make sure? Just like we did. You couldn't pick your favorite beans. You had to take a random sample. You can't pick your certain people in Iowa to ask them. You can't go to the Presbyterian church or something like that and say, hey, are you going to vote for Donald Trump? It has to be a random sample. Should you ask 3 people in Iowa? No, it's got to be a good sample. So they go in and they ask probably about 700 people in a random sample and say, are you going to vote for Donald Trump? And maybe 37% say, yeah, we're going to vote for Donald Trump. How in the world, just after one sample, can they do that? And come back and report and say, yeah, we're pretty sure this is the percent. After one sample. Seems crazy, doesn't it? What if they took sample after sample after sample after sample after sample and they graphed it? What would that distribution look like?
Normal.
It would be normal, right? So if you have a normal distribution, And now I go back and take one more sample, let's say. Where will it be approximately? Let's say this is the distribution right here. So these are voters in Iowa, and it's 27% is what we just got after doing sample after sample after sample. Now I'm going to go back and I'm going to take one more. How many should be in that sample? 27%, right? Doesn't that make sense? So, it's because of this concept that even though we're not doing multiple samples for polls, political polls, or anything else, we can just ask one sample because we know if we took sample after sample after sample after sample, we'd get a normal distribution, and our one sample would be pretty close to the center of that. Some a little farther away and some others, but most of them, as long as we have a good sample size, and does that make sense to you? All right, perfect. So that concept for the rest of the year is going to be so important. Now, there's this little confusing part, and we're going to kind of clear that up right now, that people mess up this concept between these two things. And I'm going to say it here, and you're like, what? He sounds like he said the same thing. But you need to understand the difference between the distribution of a sample, one sample, and a sampling distribution. The distribution of a sample versus a sampling distribution. They are two completely different things. So this is a sampling distribution. I'm going to write it up here. It's also down the bottom. Okay, so we know that a sampling distribution is the results of several samples. But somebody in their own words, can you try to maybe right off the bat, do you think could you explain the difference between the distribution of a sample and a sampling distribution? And maybe use the beans that we just used as an example.
Sampling distribution is a lot of them, and distribution of a sample is like one.
It's one sample, right? So let's go back to the 20 beans. On your calculator, you would just go back and look at one of those samples. And if I want to do a distribution of one sample for the weight of beans, what would I have to do for that sample of 20 beans? If I want to make a distribution or graph them, what would I have to do with my one sample of 20 beans?
A lot, like all the weights.
Yes. So this would be one sample. That is 20. And I would plot out, and I would have all 20. So whatever those weights are. So when I'm done, maybe, I got one here. I'll make a histogram so maybe it looks a little better than a bunch of dots. But maybe it looks like that. This is all 20 right here. One sample, all 20 are graphed. That's the distribution of that one sample. This is what you did in here. This is what's on the board. Mr. Murphy, that's the percent one, or this right here. If you look at this one, n equals 20 right here. That's taking each sample and finding the average for the sample and graphing it. And then doing that over and over and over again. And then when you're done, you have, so this is multiple samples here. This is the average of each sample. And when you have a large N and it was random, that will always be a normal distribution. Okay? So it sounds confusing, just changing the order of those words. Do you think they're going to try to trick you on that on the AP test?
Yes.
Of course they are. You bet. Very few questions will be about this right here. They're going to throw maybe one or two once in a while. The vast majority of work we're going to do the rest of the year is all about sampling distributions. And I saw your hand up. I don't know if you still had a question.
One sample is not the average.
Correct.
The sampling distribution is the average.
Correct.
So we made a sampling distribution.
We did, exactly. Yeah, that's exactly it. And hopefully you'll remember the sampling, we'll keep referring to this day the rest of the year. Remember we made those sampling distributions on the board? We made all. It's because of this concept that if you do it over and over, we get a normal distribution. And you only really need to take one sample to be able to get an idea of what's going on. Any other questions with that? Okay, we're going to switch to your calculator now. So grab your calculator. You entered in already into L1. The numbers, mine of course are different from yours. We're going to make a histogram. It's been a while, so we just wanted to review it. Do you want to walk through that?
So you got 10 weights in here of their 20. We did this for first hour, so remember anyone how to create a histogram? What do we go into? Stat plot. So that's second y equals, and then we're going to make sure to go up to the first one. We're going to make sure it's on. Okay, so it's on, and then we're going to go over to the histogram. Turn that on. And it should have, hopefully everyone put in their X list as L1. Okay, so you type in L1 for your X list. Frequency, just how many times does that repeat? You're always going to keep that 1. Okay, so that's the frequency is going to always be 1. And then now to graph it, remember what you hit? Maybe not. You're going to go zoom. And you're going to go zoom stat, which is number 9. Okay, so zoom 9, which is zoom stat. Okay, so then here's our histogram. Now, your calculator, does it give you nice bin widths here, usually? No, so if you ever had to graph it, that's where you're going to have to want to change that, and that's under the window. So you can kind of see, minimum, 0.27, max, 0.45. Here's your scale. You wouldn't want to use 0.026 for a scale. Okay, so we just change it into nicer numbers.
We want 5
To
to
do that.
the 20.
What's that?
Did we do the group of 5 or group of
Group of 20, we should have. Okay, so this one, instead of 0.27, I'm just going to change it to 0. Max, instead of 0.45, I'll just go 0.5. And then what do you want it to go up by? Well, what number should we go up by? What should we go up by? What's a nice number to go up by? I wouldn't
Change it too much.
I don't want to go 0.0266. Repeating. 0.02 would work. 0.025, but we'll just go 0.02. Okay. You could change the y values if you wanted to, but I don't. That's not. You're going to be able to see that pretty straightforward here. But then you can see that the graph. Now, does that look normal? Not right that much, but we didn't have enough. The more data that we put in, the more normal it would become. Okay? Your 10 points, your 10, that might not. You might not have something that's normal. Maybe you do. Okay? But the more data that we put in, the more normal it's going to become. Okay? So is there any questions as far as how to create the histogram?
It's got so long.
What's that?
Oh, never mind. Nothing.
Everyone's got that? I mean, if you have a quick question, I want to just make sure. So that's back a while.
I just don't, I couldn't even get to the list. And then,
Oh, the list?
no, I figured it out. It's in, but is there just one? Is it just L1 or is there
Yeah.
something in L2?
Just L1.
But it I don't even know what you just said.
So you got to go right there. Zoom, or sorry, Zoom. Okay. All right. Any questions as far as that? Everyone's got that? Now the other thing that they're going to ask us, is what's the average? Okay. They might ask us what's the standard deviation. Okay. Does anyone remember how to find the average and standard deviation of our values here? One var stats, exactly. So, how do I get to one var stats?
Just that over twice.
Second.
Just that and then over and then
Click stats.
So you hit stat, right? You just hit stats, and then over to calc. The one var stats, guys. You got to make sure you have that. So again, let's make sure that you got that. You hit stat, over to calculate the 1 var stats. They're going to make you do that on our homework.
What do you want for our frequency?
Still, the frequency list is just still going to be like 1. You can, because that just, all that frequency list is how many times do you want that number repeated? We only want it once because that's all we aren't going to repeat it anymore. So you just go L1. Now the older calculators, you might have to actually type in, L1 in there. And then that's all you have to do is calculate that. Okay? So here's our 1 var stats. Which one is our average? X bar. So our average, in mine, that we put in for first hour, the average weight of a bean was 0.375. Okay? And then what's the standard deviation? Talks about how spread out it is. So how spread out was it?
0.04.
So which one am I going to look at? Does anyone know the difference between the S of X and the sigma X there?
One doesn't subtract.
What's that?
One doesn't subtract one off the number of.
Okay. That's looking at the formula, Tuck. Good. But in just in general, the S of X is the standard deviation of a sample. Okay? And that's what we did. We took a sample, okay? We took a sample of them, of those beans, and every one of you took a sample. That's where the S of X, and it's always going to be a little bit bigger. That, it just give you a little bit more room for error. The other one is if you had we took the whole population. Okay, so that's the population of the standard deviation, and here's the standard. Here's the sample of the standard deviation.
Because I don't have my SX is not like, holy Jesus. My SX it's just
I have
blank.
to edit this video now. Go keep going.
Oh, sorry.
It says blank.
Yeah. No, I said shoot, didn't I?
Just.
Okay.
There it is. Never seen that.
You got individual issues. I don't know. Some strange things happen. So we have to take a look at it sometimes individually.
Your frequency list. Make sure that should work.
Any other questions on how to do the stuff
Oh,
on
you
your
just put one?
calculator?
So which one should we normally use? The S of X?
Well, you know what time we
S
get
of
done today.
X. That's the sample. That's the sample.
Shall we?
I think we got 2 minutes.
Probably a good spot to stop right here, I think. Okay, we'll finish the notes on Wednesday. And so
I will
there's
put
no
a
sign
1 into my frequency.
I would just leave it blank.
When you were saying 1, you were like, you put L1 here and then just put 1 again, and I was like,